Hi friends, welcome to today's video on our graph series. I am Chinyelu, a software engineer at Microsoft Dublin, Ireland. Today we'll be solving another medium question from Leetcode titled Clone Graph. I will start by reading the question, pointing out exactly what the question requires from us. I will then explain my proposed solution using a pseudocode so you can implement the solution using any language of your choice and get the same results. Also, I will implement this solution in JavaScript and explain the time and space complexity of the solution. Alright, let's get started. The question reads, giving a reference of a node in a connected undirected graph, return a deep copy clone of the graph. Each node in the graph contains a value int and a list of its neighbors. Test case format. For simplicity, each node's value is the same as the node's index. For example, the first node with value 1, the second node with value 2, and so on. The graph is represented in the test case using an adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a node in the graph. The given node will always be the first node with value 1. You must return the copy of the given node as a reference to the cloned graph. Constraints. The number of nodes in the graph is in the range of 0 to 100. 1 less than or equal to node.value less than or equal to 100. Node.value is unique for each node. There are no repeated edges and no self loops in the graph. The graph is connected and all nodes can be visited starting from the given node. Alright, as the title suggests, the question can be easily identified as a graph problem, and it's important to note from the given constraints that the graph is connected, which means that you can visit all nodes from any given node, and the graph is also undirected, which means that the edges indicate a two-way relationship. To learn more about this, check out my video on graph data structure. In this question, we are given a class representing a node in a graph. The class contains the node's value, which is an integer, and its neighbors, which is a list of all its edges. That is, a list of all its adjacent nodes. Similar to our previous video titled All Path from Source to Target, we also do not need to create an adjacency list since the given node is an instance of the class that contains the node's value and a list of all its adjacent nodes. And each adjacent node is also an instance of a class containing the node's value and a list of all its adjacent nodes, making the creation of an adjacency list redundant. If you want to learn more about adjacency lists and how they are created, please check out my video on graph data structure. The question requires us to create the graph, and we can achieve this by simply traversing the graph and at each node, create a copy of this node and save the node and its copy as key and value respectively in a map. We will use recursion to solve this problem. You can use breadth-first search if you wish. Understanding graph traversal is crucial for solving any graph algorithm problem, and I cannot emphasize this enough. Check out my video on graph traversal where I provided a detailed explanation on depth-first search, breadth-first search, and recursion. So solving this using pseudocode, given that our function takes a node as input, the first thing we will do is to check if this node is null. And if it is null, we will return null because null is a clone of null. Next, we will create a map to store the newly created node copies using the old nodes as keys and the new nodes as values. This will allow us to retrieve any cloned node from the map with constant time complexity. We then create our recursive function taking an input of current node. In the recursive function, we will check if the current node has been created in the map. If it has been created, we exit the function. Else, we create a clone of this node by instantiating a node class with the current node's value and assign it to a variable clone node. Then, set this newly created clone node as the value of the current node in the map. Let's assign the neighbor list of this current node to a variable neighbors and loop through these neighbors. On each neighbor, we will call our recursive function on it. After the recursive function has run for the current neighbor, we can be sure that a clone of it would exist in the map, since the recursive function creates a clone of a node if it does not exist yet. So at this point, we can retrieve this clone copy of the neighbor node from the map and assign it to a variable clone neighbor. Now, we will push this clone neighbor into the neighbors list of the clone node. We just finished defining our recursive function. The next thing is for us to call this recursive function with the given node. And finally, at the end of the function, we return the value retrieved from the map using the given node as the key, as this will be the cloned version of the given node. Great, let's implement this in JavaScript. I will now delete the pseudocode. The first thing is, if the given node is null, return null. Create map to store our cloned nodes. Define our recursive function. If the node already exists in map, return. Else, create a clone of the current node and assign it to a variable clone node. Set the current node in the map with the cloned node as its value. Assign the current node's neighbors to a variable neighbors. Use a for loop to loop through these neighbors. Call the recursive function on each neighbor. Retrieve the clone of this neighbor from the map and push it into the neighbors list of the clone node. Call the recursive function with the given node, and finally, return the value of the given node in the map. Let's run and submit the code. Great job! Let's talk about the time and space complexity of the solution. The time complexity of our solution is O of n plus e, where n is the number of nodes in the graph and e is the number of edges. This is because the function uses a depth-first search algorithm to traverse the graph, which visits each node and each edge exactly once. The space complexity of our solution is also O of n plus e, because it uses a map to keep track of the cloned nodes and their corresponding original nodes, which takes up O of n space. The recursive function also uses the call stack to keep track of the nodes being visited, which takes up O of e space, since there can be at most e recursive calls on the stack at any time. Overall, the solution has a time and space complexity of O of n plus E. Thank you for watching till the end. If this video was helpful, please give it a thumbs up and hit the subscribe button to see more videos like this in the future. If you want me to solve any specific graph problem, leave me a comment in the comment section and I will add it to my list of videos to create. Thanks again for sticking to the end. See you in my next video. Bye.